In chemistry, we deal with the infinitely small and the incredibly large, from billions of a gram to trillions of atoms. But even the most precise tools can't eliminate one thing: uncertainty. Every measurement has a margin of error. And understanding how to handle that is key to doing real science. In this lesson, we'll learn how chemists stay accurate using scientific notation, significant figures, dimensional analysis. Let's dive into the math behind meaningful measurements. Let's put things into perspective. Imagine we are trying to measure the mass of just one hydrogen atom. It's not in grams or milligrams. That's 0 point, followed by 23 zeros, and then 166 grams. Trying to write, read, or calculate with numbers like these. Yeah, not exactly practical. And that's where scientific notation comes in. We express such numbers using the format n times 10 raised to the power n, where n is a number between 1 and 10 and n is an integer. This simple format lets us work with both tiny and huge values with clarity, efficiency, and precision. Because in science, how you write a number is just as important as what it represents. Let's look at how scientific notation actually works. Example 1. Take the number 0.00016, move the decimal 4 places to the right. That gives us 1.6 times 10. Example 2. Now take 232,500, move the decimal 5 places to the left. That becomes 2.325 times 10. This format makes it much easier to work with extremely large or tiny values, especially when adding, subtracting, multiplying, or dividing in chemistry and physics. Let's take something familiar: baking a cake. That fluffy rice? It's not just heat, it's chemistry. Inside the batter is baking soda or sodium bicarbonate. As the oven heats up, it breaks down. Sodium hydrogen carbonate decomposes to form sodium carbonate, carbon dioxide, and water. The carbon dioxide released gets trapped in the batter, forming bubbles, and that's what makes the cake rise. From the texture you feel to the taste you enjoy, every transformation in your oven is a chemical reaction at work. It's not magic. It's molecular science, deliciously disguised as dessert. Let's break down the rules of significant figures so you'll always know what counts. All non-zero digits are significant. Example, 285 has 3 significant figures. Leading zeros are not significant. Example, 0.052 has only 2 significant figures. Zeros between non-zero digits are significant. Example, 2.005 has 4 significant figures. Trailing zeros after a decimal are significant. Example, 0.200 has 3 significant figures. Those zeros do matter. Trailing zeros without a decimal are not significant unless clearly stated. Example, 100 has 1 significant figure, but 100 with a decimal has 3. Knowing these rules helps ensure your measurements are not just precise, but meaningful. When reporting your final answer, it's important to round off correctly. Let's go over the basic rules. If the digit to be removed is greater than 5, increase the previous digit by 1. Example, 1.386 becomes 1.39. If it's less than 5, just leave it. Example, 4.334 becomes 4.33, and if it's exactly 5, we round to the nearest even number, a rule that helps avoid rounding bias over large data sets. Example, 6.25, 6.2, 6.35, 6.4. This may seem subtle, but in chemistry and statistics, tiny differences can matter, especially across hundreds of measurements. In chemistry, we often need to convert one unit into another, and for that, we use something called dimensional analysis or the unit factor method. It's simple, logical, and powerful. You apply conversion factors, ratios that are equal to 1. For example, 1 inch is equal to 2.54 centimeters, so to convert 3 inches to centimeters, 3 times 2.54 is equal to 7.62 centimeters. Here's the cool part. Units behave just like numbers. You can multiply, divide, square, or even cancel them out as needed. It's like doing algebra with units, and it keeps your calculations clean, accurate, and universally understood. Let's walk through a quick unit conversion using dimensional analysis. We want to convert to liters, L, to cubic meters, M superscript 3. First, remember, 1 liter equals 1000 cubic centimeters. Now, 1 meter equals 100 centimeters. 1 meter cube equals 100 to the power 3 centimeters cubed, which gives us 1 meter cubed equals 1 million centimeters cubed. Now let's convert to liters equals to multiplied by 1000 equals 2000 centimeters cubed. Next step, 2000 centimeters cubed divided by 1 million equals 0.002 m cubed, and there you have it, 0.002 cubic meters. Dimensional analysis helps you get the right answer with the right units every time. In summary, we've explored 3 essential tools every chemist relies on: small orange diamond scientific notation to simplify extremely large or small numbers, small orange diamond significant figures to reflect the precision of a measurement, small orange diamond dimensional analysis to ensure accurate and consistent unit conversions. Together, these tools help chemists maintain accuracy, clarity, and universal understanding in every calculation.